we're going to go a little bit deeper in acids and bases. So we talked about acids and bases like this. Okay, something kind of like that. Can you tell me which is my acid? What?
HCl.
HCl is the acid, and NaOH is the base. And specifically, this is called a neutralization reaction. We good? Okay. So I gave you the definition of acids and bases based off of one guy. His name's Arrhenius. We don't have to know his name. But today we're going to talk about a different definition. Slightly different. Some of it's similar. But just so that you know, if you go through and you read something, say, what the heck is that? I can just give you the name. I'm not going to test you on it, but like on homework, it might be there. Oops. The Bronsted-Lowry definition. So what they said is an acid is a proton donor. We know what a donor is. Somebody that gives something away, right? So we're donating a proton. Doesn't mean what it sounds like. We're not giving a proton to the nucleus of another atom. Okay? If we take a hydrogen atom and rip off the electron, what is it? Well, let's draw it. Here's a proton. Here's a hydrogen atom. Hydrogen atom has one proton, and most hydrogen atoms don't have any neutrons. Then we have an electron buzzing around. If we remove that, we're just left with a proton. So this proton basically, or is, an H plus ion. And we kind of already knew that about acids and bases, right? So we said HCl is an acid because it has an H plus as the cation, right? And this is a base because it has an OH minus as the anion, right? Okay. But for our new definition, acid is a proton donor, so it has an H plus that it could get rid of, could donate. Okay? And so it's kind of the same thing as far as the acid goes. The base is a proton acceptor. And again, our proton is the H plus. So basically, an acid is any compound, any substance that has an H plus in it as a cation. Any ionic compound with H plus as the cation. Now there is an exception to what I just said there. Always, right? H2O is an example of an acid. Okay, that doesn't have an H plus as a cation. That's the covalent compound. Are you with me? But I think that's the only exception for acids that doesn't really follow that. But anyway, we'll get there a little bit more. So things like HCl, H2SO4, these are acids, right? Because they have the H as the cation. Good? One thing we need to remember from before, acid must be an aqueous solution, right? A base must be an aqueous solution. If it's not, then it's just a salt. It's not an acid or a base. But as soon as you throw that salt in water, it becomes an acid or a base. Good? Y'all remember this from a few units ago? Okay. And so what is a base? Not quite. So it's a proton acceptor, we call it. So, but it's any anion in a solution of water. So again, it has to be aqueous, okay? Why an anion? Anions are negative, and if it accepts a proton, which is an H plus, which is a positive charge, negatives attracts the positives. You with me? That's why. So, for example, there's two exceptions for this. One of them is H2O. Oh, hold on a second. That's a base and an acid. Okay. Another one is NH3. This is also a covalent compound. Ammonia is a base. So what? We'll get there, okay? But if we list some other examples, we got NaOH. Is that a base? If it's in water, it's a base. Because what happens if it dissolves in water? It dissociates and we have a hydroxide ion that's negatively charged, and it can take in a hydrogen ion. You with me? Okay. So like I said a minute ago, acids and bases must be aqueous. If we don't have water, we don't have an acid or a base. Okay? So let's, not yet. Does that make sense to everybody, or should I show you a little breakdown of an acid and a base? Okay, here we go. So an acid is like HCl, maybe as a gas, plus H2O as a liquid, and it becomes H plus in aqueous solution plus chloride in aqueous solution. There is the proton that it can donate. Good? And it will donate it if it's with a base or any other negative charged particle, which is a base. Good? And then a base, for example, is NaOH, maybe as a solid, plus liquid water, gives us sodium in aqueous form, plus hydroxide in aqueous form. And here is the base that can accept that hydrogen ion. So what do you think? Is that a base? Is NaCl as a solid? Salt. Is that a base? No, it's not. But if we throw it in water, is it a base? Yes, because that becomes Na plus and Cl minus. And that negatively charged ion becomes an acceptor of a hydrogen ion. Good? Questions?
So you don't have to, you don't need to produce H2O.
What?
H2O. So,
Well, aqueous means it has water in it.
okay.
Remember? Remember that? Aqueous means it has water in it. It's dissolved in water. It's a water solution. How are we feeling with the new definition of an acid and base? Any questions on this? Please say something if you're not quite getting it. Okay, so make sure we study this. Another term is amphoteric. Amphoteric is a compound that can be both an acid or a base. So let's do some examples. We just talked about one, water. Can be both an acid or a base. HSO4 minus. It has the H in front, that's the cation, that's the H plus. That's why it's an acid. Why is it a base? Any ideas? What makes it a base? It's negatively charged. That means it can attract an H plus. Are we good? So anything with a negative charge is a base. If it has a H plus ion in it, it must be an ion, except for an NH3. Then it's amphoteric. Good? Okay, let's take a look at section 1 on the worksheet that you picked up. It says, identify the following substances as acids, bases, or amphoteric. Should we do these together? Or do you want to do these alone? Alone? Go for it. And I did put back there, study guide to exam 5, which is on the 9th of December, and a study guide to the final exam, which is on the 16th of December. That means we have 3 class periods before exam 5.
Is the final in class?
The final is in class as well. Yep.
Sorry, when's exam 5? December?
Exam 5 is December 9th.
So it's
That's,
Finals
weeks.
yeah, the final is a week later on the 16th.
Does the final count just as an exam in
Yep.
the grade book? Okay.
That's why if you miss it, that's the one you drop. Right? So if you're happy with your grade after exam 5, you can miss the final exam. If you want to take it just to see what you know, great. Then we can drop a different exam, right? Maybe. I've had students come in and ace the final, and it brought their grade up. And I've had students that don't do well in the final, and then we just knock it out. But if your grade is iffy and you get ready for that final and you show me that you know it and understand it, that's to your advantage. That's all I'll say.
Can we still do the ice cream extra credit, or is that too long gone?
Sure.
I guess can we do the final in the testing center, 16th, that would not be around.
Yes, I will put it in the testing center. In fact, I'll probably put both exams, exam 5 and the final exam in the testing center if you want to take it there. I'll also have it in class on the 9th and the 16th. That way, I mean, it's the very end and I know stuff gets crunch time, but sound good? But the exam 5 can't be taken after, I think, Thursday or Friday of that week, because then next week is final exam week.
So the final opens on the 15th.
Yeah. Sorry, I'll just shut up. You guys are trying to do your stuff, right? Any questions on section 1?
Do you have answer?
Yeah. Any questions? All right. If we don't have any questions, let's talk about strong acids and strong bases.
Why NH3 is an exception?
What's that?
Why NH3 is an exception for?
Why is NH3 an exception? That is a good question. Why is it the way that it is? Really? Why is it different than the rest? Kind of like, why is water an acid and a base? Because the way that it is. No, we don't know all of science. We don't. We just see, okay, it does the same stuff that bases do, so it's a base.
Okay.
Sorry.
So is that something we need to memorize then, the NH?
Yes.
Okay.
The NH3 is a base. You need to know that. NH3 is ammonia. You guys deal with ammonia in real life? Okay. And really, bases are like soaps, and a property of a base is it's slippery in touch. It's bitter in taste. I mean, don't go and just taste stuff. Well, yeah, that's a base. But, and acids are sour, okay? And not slippery, but sour, okay? So anybody taste ammonia before? It's probably bitter, a little bit slippery, okay? All right, let's talk about strong acids and strong bases. And this is going to kind of tie into our solubility chart. Okay? So we got strong acids and strong bases. And really, there's only one strong base, and it is anything with hydroxide. We kind of already learned that, right? When we have a neutralization reaction, we're dealing with a strong acid and a strong base. Okay, they completely neutralize one another. And how is it that this happens? A strong acid and a strong base, they completely dissociate in water. So if we have, let's look at the strong acids real quick. So HCl, HBr, HI, HNO3, H2SO4, and HClO4. And if you memorize the strong ones, we know the weak ones. And there's less strong ones. So memorize these. Here's how I kind of remember them. If strong acids and strong bases dissociate completely, that means they're highly soluble or highly insoluble?
Soluble.
Highly soluble. So look at our solubility chart. Chloride, bromide, iodide are halogens, and they are soluble. There are a few exceptions, but is hydrogen one of those exceptions? No. So it's going to dissociate completely. I mean, there are exceptions, but hydrogen's not an exception. Good? Nitrate is soluble without any exceptions. Sulfate is soluble with some exceptions, but hydrogen is not one of those. And perchlorate is soluble without exception. Cool. You with me? Since it's soluble, It's gonna dissociate 100% of the way. And since it dissociates all the way, that means there's a lot more H pluses in there. That's what makes it a strong acid. Good? Strong base, hydroxide. Hydroxide with almost anything. Not everything, but we'll just keep it simple here. Okay? Any questions about strong acid, strong base? All right. So let's do some acid-base reactions to kind of make sense of this a little bit. So if I start with a,
Question.
yeah,
So C2H5OH, it is not dissociable, right?
C2H5OH, C2H5OH, that one is ethanol. That's not an acid.
So it is a strong base?
Because it has OH in it? No, that's not a base either. That's an alcohol.
But it has OH.
Oh, okay. Does it have OH minus?
Oh,
What compounds have OH minus? Ionic or covalent?
Ionic.
Ionic compounds have OH minus. And C2H5OH is covalent.
So is that the same reason why ammonia, because that doesn't dissociate in water?
I mean, ammonia it doesn't dissociate, but it dissolves in water.
Right.
Yeah,
But all on its own, not
Uh-huh.
splitting.
yeah. We good? Great question. So yeah, this has to be from an ionic compound. Okay? Okay, so if we start with the neutralization reaction, we kind of already wrote one of those. I could write the same one we did. HCl. And I'm going to just omit the aqueous. Is that okay? We know if it's an acid base, it's got to be in water solution. Okay? Plus NaOH. And we get water. And if we have water, then they're aqueous. Plus NaCl. So here we have a strong acid, one of our strong acids. And here we have a strong base because it has OH minus in it. Remember, if it is aqueous, it will dissociate and be the OH minus. Okay? And then we get water and salt. And this is the type of reaction we did a long time ago when we talked about acid-base reactions. Good? And we'll come back to this a little bit. I just wanted to put that out there. So that's our neutralization reaction. And so if we're told that our acid-base reaction neutralizes, or acid neutralizes with a base, then it's going to look similar to that. It's going to be water and salt. It's a double replacement reaction. They swap partners. You remember this? Okay. All right, we'll do some examples that kind of help us to see that a little bit. Okay, let's do another one. H2SO4. All right, aqueous. Just so that, anyway. H plus H2O as a liquid gives us HSO4 minus aqueous plus H3O plus aqueous. Okay, water could be an acid or a base. What is it in this equation?
Base.
How do you know?
Well, because the other one's an acid.
Oh, because this one's an acid.
Yeah.
Make sense? So here's our acid, and here's our base. Now let's see another way to know that this is our acid. What does H2SO4 turn into in our products? HSO4 minus. Do you get that? It is most like it. So this acid becomes this guy. And what happened to it? It lost an H plus. It donated a proton. You with me? And a base is a proton acceptor. And what does it turn into? H3O plus. Well, H3O plus is just water with another hydrogen in it. So that is a proton acceptor. You with me? So this acid turns into a base. And this base turns into a acid. Is this an acid, H3O plus? H plus H2O as a liquid gives us H3O plus. This is hydronium ion, but it's basically the same thing as that, isn't it? If we were at H plus aqueous, that means it's H plus with water in it. That's basically what that is. Well, it is what that is. Okay? So sometimes we use H plus and sometimes we use H3O plus. They're the same thing. Okay? So this HSO4 minus, this is called our conjugate base. And this H3O plus is called our conjugate acid. An acid becomes a base, and a base becomes an acid. You with me? Maybe write that down. Acid becomes the conjugate base. And the base becomes a conjugate acid. Doing okay? Does it do that on a neutralization reaction? Let's see. So here's our acid, HCl. And what does HCl turn into if it gets rid of an H? NaCl. Well, hold on, this is aqueous, right? Is it really NaCl or is it just Cl minus? Right, it's dissociated because it's aqueous. It's dissolved in water. So basically it's just a Cl minus ion. So this is our conjugate base. Because anything that has a negative charge on it is a base. And this, our base, which is NaOH, turns into, oh, does that turn into water? If it gains an hydroxy, or a hydrogen ion? Remember, this is an aqueous. It splits. This hydroxide is the base, and it grabs onto a hydrogen ion and turns into water. So water is our conjugate acid. Do you get that? Or is that, oh, funky?
The water.
Yeah, so water is the conjugate acid because the hydroxide accepted a hydrogen ion and turned into water. So this sodium is there, but is it really participating? Remember we called that a spectator ion? It's not really participating, it's just there in both cases. You throw that sodium hydroxide in water and it dissociates. And then it does its reaction and it's still there, dissociated. So that's kind of like to hide the agent, right? Okay, I don't know. We good? Questions?
OH accept H
Uh-huh.
plus becomes to
H2O.
H2O.
That's it.
But it is a proton acceptor, so it is a base.
That's right. And then
You said it's conjugate
this is not a conjugate acid.
acid.
The water is a conjugate acid. Can the water be an acid and a base? Yes. In this case, it turned a base turned into an acid. That's what makes water an acid sometimes. Now, in reality, do we think of water as an acid or a base? No, it's right smack in the middle. It's neutral. But it acts as both an acid or a base. Sometimes a base turns into an acid, sometimes an acid turns into a base. And that base, that could be water. Good? Should we do one more? Okay. Let's see if you can do this one. HSO4 minus plus H2O as a liquid in equilibrium with SO4 2 minus plus H3O plus. This time, our reactants are both amphoteric. You see that? Anybody not see that? Okay. So which one's the acid, which one's the base? You gotta see what it goes to. So this HSO4 turns into what? What is most like what is most like HSO4? SO4 2 minus. And what does water turn into? Oh, it's most like H3O plus. So which one donates the H plus? HSO4 minus. This is our base. Sorry. This is our acid. And it turns into a conjugate base. And this can't be an acid because there's no H plus in it. You with me? And our base has to be the water, and it turns into our conjugate acid, which has an extra H plus it can get rid of. How are we feeling? Like I put you in the blender and stuck you on high, or are we okay?
So if you got the first half of that equation, you wouldn't be able to determine, you'd have to have the whole equation
Yeah. I mean, you can guess, but
Right.
should do some more? Thinking we need to. Let's do it. So we have HCl plus NH3 gives us NH4 plus and Cl minus. Which one is the acid? Yeah, this one can't be a base, so that's our acid. And this one can't be an acid, so that's our base. If we know that NH3 is a base, right? Then we need to know that. So what does the base turn into? Or sorry, the acid? Cl minus. It donates an H plus. That makes Cl minus what? Conjugate base. The acid turns into the base, and the base turns into an acid. We know that's an acid because it has an extra H plus sitting there. You follow?
And semantically, conjugate just is meaning like after the combination of donation.
Yep. It turned into an acid or a base. Yep. Do we need another one, or are we? How are we doing? I'm seeing a no. Talk to me. Here for you guys.
We're doing off the sheet.
Yeah, let's do it. Okay, section 2. Identify the acid base, conjugate base. Are you saying, can we do one off the sheet? Like we, or you? I'm sorry. Okay. Why don't you try it? You want to try number 1 and then we'll do it after you're done? And if you feel like you got it, do number 2 and then number 3. And then I'll give you the answers to make sure we got this.
For one of the questions,
Uh-huh.
we identify it as an acid even if it was
Amphoteric?
amphoteric, but it's acting as an acid in the
Yep.
end? Okay.
That's right. Because in that reaction, it's amphoteric, or it's an acid, right? Any questions? Okay, let's move on.
Can I see the answer?
Yeah, just a second. Good? All right. You guys remember stoichiometry? Going from one substance to a different substance using dimensional analysis? With moles, grams, and all that stuff? Okay. What does A stand for? Whatever you want. Or we can have it stand for an acid. And what does B stand for? Base. You with me? So when we're going from an acid to a base or a base to an acid, there it is. And we do the exact same thing. Good? Okay, so we're going to still use that. Now let's do we need a refresher on stoichiometry, or should I just jump to an acid-base one? Acid-base? Okay. Okay, we have HCl plus calcium hydroxide gives us H2O and calcium chloride. What kind of reaction is this besides acid-base?
Neutral.
Neutralization reaction, because we get salt and water. Okay? Now what should we do before we do anything else when we do stoichiometry? Balanced equation. So we have 2 chlorines right here, so I'm going to put a 2 in front of that. Now let's do calcium's okay. Oxygen, we have 2 on this side, so I better put a 2 right there. Oxygens, we got 4, so I better put, there's a 2 there and a 2 there, we're good. Good? Okay. So now let's do this problem here. How many liters of a 0.125 molar concentration of HCl would react with 350 milliliters of a 0.200 molar concentration of calcium hydroxide? Okay, what are we looking for? Volume, right? Liters of my acid. Can y'all see that this is my acid and this is my base? Okay, so we have to be able to do that. Now, I have information. What do I have more information for? Acid or base? Base, so that's where we start. Start with my base because I know everything about it. And I'm looking for my acid. Does that make sense? Okay. So let's start with, do you want to start with 350 milliliters or 0.200 moles? Molarity. It doesn't matter. Let's just start with 350. Okay, that's done. I'm not going to use that anymore. Remember, molarity can be written as what?
Mole volume.
Moles per liter. Yeah. Okay. And it's per liter, so we have to change milliliters into liters. 1,000 milliliters to 1 liter. And now I use my molarity, 0.200 moles of calcium hydroxide to 1 liter of solution. Y'all with me? Do that so that the units cancel out that I don't need. Okay, now I have moles of calcium hydroxide. What am I looking for? Liters of a different substance. Liters of HCl. So what do I do now? Mole to mole ratio. And if you want, you can find an answer and restart. Your call. I'm going to just keep going unless you don't want me to. We good? Okay. So what's the mole to mole ratio? 2 to 1. So 1 goes where? On bottom, 1 mole of calcium hydroxide to 2 moles of HCl. That goes away. And I'm looking for volume. So now what do? I have molarity, put it in moles per liter. What goes on bottom? Moles. 0.125 moles of HCl per 1 liter of solution. That goes away. And I'm left with liters of solution. And I got 1.12 liters of my HCl solution of the 0.125 molar HCl. Was that too much? Yeah? Maybe I should show you a modified mole roadmap. You don't get it on the exam, but you can get it down and draw it on the periodic table when you get it. Practice drawing it. You're ready for the exam. Should be okay. So here we go. All right, I'm starting where on this? I'm starting with my concentration of my base, right? Here it is. Molarity of my base. And what can I do to get to, I'm looking for volume of my acid. So what do? Follow this arrow. I multiply my volume by the concentration, and liters goes away, right? Then I have moles of my base. Then I do mole to mole ratio from balanced equation. I have moles of A. And so you see how these are kind of flip-flopped? So depending on what you want, if you want liters, then you're going to multiply or divide by molarity. And if you want molarity, you're going to multiply and divide by liters. Sound good? That's it. There's our path. We'll learn this later today. Okay? This is actually easier. because there's formulas on your reference sheet that you don't have to memorize. We good? Do you want to do it on your own?
Okay.
Or do you want to do another one together? I'm having one person tell me on their own. Is everybody in agreement with that? Okay. So I'm going to take this same equation, 2HCl plus calcium hydroxide gives us 2H2O plus calcium chloride. Okay. I want to know the concentration. What is the concentration of HCl if I have 750 milliliters of my HCl solution that react with 350 milliliters of a 0.200 molar concentration of calcium hydroxide. If we look at the mole roadmap, can you erase some of this stuff? Start again. What do I know most of? The base again. So I'm going to start here again. And this time I want to know my concentration of the acid. So I'm going to do the same thing, but it's not choppy. Do you have to use the molar roadmap, you guys? You do not. If it confuses you, throw it out. So start here again. And go to here. Thank you. Do we all know where to start? Where's a good place to start? We know everything about our base. Start one of those numbers. Does it matter which number? No, it does not. Start with one of them, make sure you have units. Try to cancel the units that you don't need. And do it until you get the units that you do need. It's kind of the same as the last one, slightly different. Anybody starting with 350 milliliters? Or who's starting with 0.2 molar? Do you want to start with 0.2 or 350?
350.
Okay. I like to start simple, but it really doesn't matter. Remember, molarity is moles over liter. That's 2 units instead of 1. So what do I got to do first?
Change to liter.
Change it to liters because I have moles per liter right here. And if you want to do that separately over here, you can. Oh, let's just do that. 350. In fact, we could just do that first, right? 1,000 milliliters to 1 liter. And we get 0.35 liters. Then we can start with this. 0.35 liters. Is that better? Okay, let's do that. Then we have molarity. 0.200 moles of calcium hydroxide to 1 liter of solution. Do we all get that step?
Why it is 0.2 molarity and then change to mole?
Molarity is moles per liter.
Oh. Yeah.
Yeah, just take that molarity out and put moles per liter. Whenever we use dimensional analysis, that's how we must do it. Because molarity won't ever cancel with anything. Good? And we can find an answer here. If you want to do one step at a time until you get there, that's okay too. Anybody want to do that? Okay. I have mixed feedback, so I normally just do one thing, so I can just do one step at a time. So what's 0.35 times 0.2 is 0.07 moles of calcium hydroxide. Y'all with me so far? So I'm going to start with what I have at the end, 0.07 moles of calcium hydroxide. And now that I have moles, I want to get to a different substance. You get the moles, then you use the mole-to-mole ratio. And what's the mole-to-mole ratio? 2 to 1. So 1 mole of calcium hydroxide goes on the bottom so that they cancel to 2 moles of HCl. And I get 0.14 moles of HCl. Is this what I'm looking for? No, so I keep going. I'm looking for concentration, moles per liter. I have a volume of my HCl solution, so I better change my 750 milliliters into what? Liters. 1,000 milliliters to 1 liter. And I got 0.75 liters. So now I have my moles and I have my liters. I can find concentration in molarity, moles divided by liters. 0.14 moles to 0.75 liters. And I should get 0.187 molar solution of HCl. Is that right? And if you'd like, you could just do that in one long out stretch problem. That's the way I like to do it. But if it helps you to not pull your hair out and just say, oh, what do I do? Just do one step at a time. Okay? Questions?
Let's do another example.
Another one? Okay, on your worksheet. Let's see. Section 3. 1, 2, or 3, your choice. Do them all. But we're not going to wait for you to do them all because we got to get some stuff done tonight. Do y'all want to do one more? Okay, let's do it. Okay, this one says how many moles of HCl will react with 32 milliliters of our concentration? Kind of the same thing we've been doing, right? If you want to go one step further, number 2, how many grams react with that? So you got to go one more step, moles to grams, right? And then the last one is we want to know the concentration that will react. That's one we just barely did. Which one do you want to do? Number 2. Pick 2, my lord. Wait, it's 3. Okay. Okay, do you want to do it together right now or just on your own? Okay, do it, and I'll give you the answers.
So we need to write an equation for this one?
You mean dimensional analysis? Oh,
Like
maybe.
H3PO4 plus
Yeah.
H3.
Yeah, we're going to need to know the mole-to-mole ratio, aren't we? So it says calculate the following problems. So number 2 says how many grams of H3PO4 will react with?
But the equations are from part 2.
Oh, yep.
Oh.
The equations are the same ones from part 2.
Mm.
Yeah, I wouldn't expect you to do that.
Reverse engineer first, yeah.
Not that one. Good catch. And it tells you to do that if you just read, huh? Readers are leaders. So 0.75 liters of NaOH at one concentration, so I want to know the concentration of my NaOH, will react with 59 milligrams of HBr.
So it's just, what does it mean to the point where like they're equaled out? Like they neutralize or?
We're just doing stoichiometry.
Okay.
So if I have 750 milliliters of this substance, I want to know how many milligrams of this substance will react completely. Yeah. Does that make sense? And you don't really, it's, so you gotta convert them to moles and moles, right? Okay, just a minute or so left, and then we'll move on. Any questions? Moving on? Okay. Okay, now let's talk about pH. Anybody know what pH stands for? We know it has to do with acid and base, right?
Yeah.
Okay. pH is the power of the hydrogen ion concentration. Great. What the heck does that mean? Okay. So the pH scale goes from 0 all the way to 14. Where the 0 end, that's the acidic side. And the 14 end, that's the basic side. Good? What's right smack in the middle? 7. That's neutral. That's where water is. Good? So the first equation that we'll give you, pH is equal to negative log of the H plus concentration. Remember in bracket that means concentration? Generally in molarity. But it really, yeah, it needs to be molarity. But how many times do you know the concentration of H plus? Probably next to never. Okay, so we're going to eventually get there. Okay, we're going to start simple, and then we'll get into a real problem. And we could also find the POH. What do you think the POH is? The power of the hydroxide ion concentration. And that's equal to the negative log of the hydroxide ion concentration. Anybody ever heard of a POH before? Yeah, that's goofy. We never check the pOH, so we use it to help us calculate the pH. Because maybe we don't have, maybe we're dealing with a base. We have the concentration of our base. But how do we calculate the pH? Using the pOH. We'll get there, one step at a time. Okay? So far, we'll just start with this simple equation. You guys all have a scientific calculator? So are we doing logarithmic math today? No. I'm just showing you how to use a log function on your calculator. Simple, simple, simple. It's like multiply, guys. Maybe a little bit more complicated, but just a button. Okay? So we're not going to get into the math of logs. Promise. Okay, so let's do an example using this. What is the pH of a solution that contains 0.015 molar of H plus? Again, this is not a real problem, but we're going to start simple. So pH, we're looking for pH, and that's equal to negative log of my hydrogen ion concentration, which is 0.015. So we type this in our calculator, and I want to make sure everybody can use their calculator and get the correct answer. We should get 1.824. And what are the units? No units. Woo-hoo. Can we all do this? Try it. If we're not getting it, some calculators are a little bit different. Most calculators, you just type in the negative button, log 0.015. If that's not working for you, it might be a reverse polar thing. You have to type in 0.015, then the log button, then the negative button, or the plus minus button. Okay? Anybody struggling with this? Okay? Then let's move on. And you could do the same thing if you have the hydroxide ion concentration, right? But that's the pOH. We'll get to problems like that in just a minute. Let's just make it a real problem now. That was pretend. Let's do a real one. What is the pH of a 0.0125 molar concentration of HCl? Now what? How do we find the H plus ion concentration? Because we have to have that to find the pH. Oh, just give me a pH strip and I'll find it, right? Okay. So we got to change the 0.0125 moles of HCl per 1 liter of solution. Y'all with me what I did? Just change molarity to moles per liter. And now I got to change moles of HCl into moles of H plus. Can you all do that in your head? What goes on the bottom? 1 mole of HCl. How many moles of H plus, guys? 1. Oh, how can we see that? If we have one of those, if we have 1 molecule of HCl, how many hydrogen atoms do we have? 1. So do we got to convert moles to particles to moles to particles to moles? What do you think? No. That's the whole beauty of 6.022 times 10 to the 23. We don't have to. It's the same number for every substance. So we can just say, for every 1 mole of HCl, we have 1 mole of H. Do you remember doing that proof? We don't have to use 6.022 times 10 to the 23. We're done. Since this is a 1-to-1 ratio, that's it. What if we was dealing with H2SO4? Now what's the mole-to-mole ratio? For every one of these, we have how many hydrogens? 2. That's a 2-to-1 ratio. So we got to look what we're dealing with. We good? Okay. We can erase that because we're not dealing with H2SO4 here. So since that's 1, well, that doesn't change. So the hydrogen ion concentration is now 0.0125 molarity. You with me? So now we do pH is equal to the negative log of this, 0.0125. Good? And we should get 1.90. Questions? Okay, let's move on to the next equation. Yeah.
Can you show again how we get the 1.90?
Uh-huh. Negative log of 0.0125. What?
In the calculator?
Yes. Can you do that? Try it. Make sure you can do this because we want to make sure we can do that right now before we get, and you can't use that one on the test, so I would use your,
Yeah, I don't know.
oh, okay. Let's find one.
Yeah.
Okay. Okay, so the next equation is going to help us to go from POH to pH. Because we do that same thing with POH, right? Maybe we have the concentration of sodium hydroxide. Can we find the concentration of OH? Sodium hydroxide. What's the ratio of sodium hydroxide to hydroxide? 1-to-1. So whatever our sodium hydroxide concentration is, that's what our concentration of our OH is. And then we find the POH. Now how do we go to POH to pH? Here it is. pH plus the POH is equal to 14. Why is it 14? Because that's our pH scale, 0 to 14. Okay? And so this is what we get on our reference sheet, this equation. What if we want to solve for the pH? What do? Subtract POH to both sides, and we got 14 minus whatever POH is. Or we can do the same thing and find POH is equal to 14 minus the pH. Why would we do that? We'll find out. We'll do some problems. Maybe not today, but we'll get there. Okay? So sometimes we go one way, sometimes we go another way, depending on what we're looking for. Ready for an example? Am I going too fast? Okay. What is the pH of a 0.0105 molar concentration of magnesium hydroxide? We're looking for pH. Should we start with what we know? definitely. What do we know? An acid or a base? Or more, do we know H plus or OH minus? We're dealing with OHs, right? So we got to start there. Maybe we got to find the POH first, right? Because we have a base. And POH, does that make sense to everybody?
Yeah.
POH is negative log of my hydroxide ion concentration. I don't have that. I have my magnesium hydroxide concentration. And what's the ratio to magnesium hydroxide to hydroxide? 1 to 2. Do you see that? So I'm going to write it out. 0.0105 concentration of Mg. In fact, I'm going to just write it out. Moles of MgOH2 to 1 liter. And I got to convert moles of MgOH to moles of OH. And we know for every 1 mole of MgOH2, I hope we know this. If we don't, we should tell me. To 2 moles of OH minus. Are we good? Questions? So that goes away. And so we just multiply this by 2. And that's our hydroxide ion concentration because we still have liters, moles per liters. So that's going to be 0.021. Is that right? Molar concentration of hydroxide. Now we can plug this in here. And we get our POH is equal to, I think I did this wrong on my notes, so maybe you guys do this for me. Negative log of 0.021. What do we get? 1.68? I did do it right. My last class fibbed. Okay. 1.68. Okay. Is this what I'm looking for?
No.
Oh, no. So make sure we know what we're looking for. So we got to find the pH.
14
pH is equal to 14 minus the POH, 1.68. And that gives us 12.32. Is that acidic or basic? Basic, because it's closer to the 14. And should it be basic? Yeah, we're dealing with a strong base, hydroxide. You with me? And on this last one, last 2, we had a pH of 1.9. Is that acidic or basic? Acidic because we're dealing with HCl. That's a strong acid. That makes sense. We good? Questions? All right. One more thing before we leave tonight. Okay? We're going to do the inverse calculation to pH. I'm not going to show you how it works with the logarithmic scale. I'm not going to. I'm just going to give you the equation because that's what you get on the reference sheet, right? Unless anybody wants it. Please say yes, please say yes. I'm just kidding. I won't show you. All right. So the inverse calculation of the pH is maybe we don't know maybe we know the pH, but we don't know our concentration. So we know that pH is equal to negative log of the H plus ion concentration. If we do a little bit of logarithmic math, then we'll get this equation. The H plus ion concentration is equal to 10 to the negative pH. Because log is basically base 10, right? Okay, we're not going to worry about that. Calculator is base 10. We're going to just keep it simple. And that's the equation. Can we do the same thing with hydroxide ion concentration? 10 to the negative pOH. So we get both of those equations on your reference sheet. Okay, so let's practice this. We good? How many moles of HCl are contained in 850 milliliters of a solution with a pH of 3.2? Okay, where do we start? We want to know moles of HCl. That's what our question is. And we have two values. 800 milliliters of a solution with a pH of 3.2. Does it matter where we start? Let's find out. Let's start with 850 milliliters, see where that takes us. What can we convert that to? Liters, sure. We got liters. And we got 0.85 liters. What can we convert that to? We don't have anything else. Maybe it does matter where we start. But that's okay. This might be useful. We didn't waste our time. We just can't use it yet. Right? No big deal. So let's start with, let's do the hydrogen. We're dealing with an acid. So it's okay to stick with acid, right? We're not dealing with a base. We're not dealing with hydroxide. So hydrogen ion concentration is equal to 10 to the negative pH, which is negative 3.2. You with me? And that gives us a concentration of 5.36 times 10 to the negative 4. No, that's not right. I got ahead of myself. 0.00063 molar solution of H plus. You with me?
Is
Okay.
that why there can be negative pHs, is because there can be a higher concentration than one? H plus?
Yes. Okay. All right. But hold on a sec. I'm looking for moles of HCl. Can I convert that to molarity of HCl? Yeah. What's the ratio? 1 to 1, right? 1H to 1 HCl. So can I just call that HCl? Yeah. And if I don't see it, then just do it. Who wants me to just do it? Yeah? Okay. So I'm going to 0.00063, and I'm going to change this to moles of H plus to 1 liter. Is that okay? I just changed molarity to moles per liter. And in HCl, I know there's one of those to every one of those. 1 HCl to every 1 H plus. So 1 mole of H plus to 1 mole of HCl. That goes away, but gosh, Multiply 1, divide 1 doesn't change it. So that's why I could just change H plus to HCl. Y'all with me? Okay. But I want to know how many moles. I'm looking for moles, not molarity. But I do have my liters already. So 0.00063, and I'm going to change it back to moles of HCl to 1 liter. I did all that, and I didn't have to. You follow me? If you can see that. If you can't, just do it, no big deal. Now I'm going to multiply by what? Liters, to cancel liters. 0.85 liters. Liters goes away, now I have moles of HCl, and that's what I'm looking for. And so I get 5.36 times 10 to the negative 4 moles of HCl. We doing okay? Making sense? Should we go back to the mole roadmap again and see how we can use it? Again, you can only use it if you can make it. And I'll send you guys a PDF of this. So where did we start here? We started with our pH, and we wanted to go to moles of acid. We started with our pH of our acid. I do 10 to the negative pH to get molarity of my acid, and then I multiplied by the volume to get moles of my acid. That's it. You with me? Should we do one more or kind of put it all together? Last one. You guys do titration in the lab yet? Okay, so that's basically what we're doing here. So if 3.5 liters of an HCl solution with a pH of 3.4 is needed to neutralize 58 milliliters of sodium hydroxide solution with an unknown concentration. What is the concentration of our sodium hydroxide? And it doesn't give us an equation. Can we write an equation for this? What reacts? What two things react? HCl and NaOH. They neutralize. This is a neutralization reaction. What do we get? Water and, oh, what's the salt? NaCl. These just swap partners, right? It's a double replacement reaction. Is it balanced? Yes, so we're good. So where do we start with, an acid or a base? We're looking for the concentration of my base, right? So I'm going to start with my acid. Okay? I have my pH, so I'm going to start here. And I'm going to go to my concentration of my base. I'm going to end here. So I follow this path. That's it. Okay? And again, you don't have to have that mole roadmap. So let's just start. We have pH. What can I find if I know my pH? My H plus concentration. And it's the pH of my base. Sorry, of my acid. So I'm finding H plus. If I had the pH of my base, I would have to find the OH first. You with me? Just do one step at a time, but just make sure you're watching what you have. So this is 10 to the negative 3.4, and that's going to give me 3.98 times 10 to the negative 4. Can I just change this to HCl? Is it a 1-to-1 ratio? Yeah, I could just change that to HCl. So now I have 3.98 times 10 to the negative 4, and I'm going to change this to moles over liters of HCl. You follow me? Okay. And I have my volume to get rid of liters, so I'm going to multiply 3.5 liters. And now I can use the mole-to-mole ratio, because now I have moles of HCl. Mole-to-mole ratio in our balanced equation is 1-to-1. Well, that's nice. 1 mole of HCl to 1 mole of NaOH. You follow me, or am I going too fast? I can slow down. Talk to me. Okay? So I have moles of NaOH, and I have volume of NaOH. Can that give me molarity, concentration? Yes, but I have to change this into liters. So let's do that right here. 58 milliliters, 1,000 milliliters to 1 liter gives me 0.058 liters. So now I'm going to just divide by 0.058 liters. Now I have moles per liter. And that's what I'm looking for. And I get 2.4 times 10 to the negative 2 molar concentration of NaOH. Okay? Was that a lot? Both? So we're just using dimensional analysis, and I know it's a lot of steps, but don't get overwhelmed with it. Just do one step at a time. Use your equations on your reference sheet. Use your calculator, one step at a time. Sound like it burned a lot of you guys out, some of you guys out. Go back and watch this video and look up Khan Academy. Read your book. Take the time. Get good at it. We're just using dimensional analysis, guys. When I say just, I'm not saying it's easy. I'm saying that's what we're doing. Have a happy Thanksgiving and be safe. See ya next week.